Welcome to Stony Brook University Preview Week. We're happy that you've joined us for today's presentation, The City of the Future, Reimagining and Reinventing Civil Infrastructure. I'm one of your hosts, Amanda Mills, Assistant Director of Admissions. Today's presentation is being recorded and will be available for viewing on the Admission YouTube page later this week. Also joining me from admissions is Ryan Donnelly, who will be monitoring the Q&A during the presentation with me. Please use the Q&A to ask questions for our presenters, and we will save time at the end to answer them. You can find the Q&A at the bottom of the Zoom webinar screen. Now, please join me in welcoming our panel from the Department of Civil Engineering.
Thank you, Amanda, and good evening or good morning. I believe some of you might be joining us from China. That's what I told. And we are very thankful that you chose to attend today's session. My name is Rigoberto Burgueno. I'm a professor and chair of the Department of Civil Engineering here at Stony Brook University. And I'm joined by two of my colleagues, and I will let them self-introduce. First here joining in the room.
Hello, everyone. My name is Paolo Celli. I'm an assistant professor here at Stony Brook since, I believe, January 2020. And my area of specialization is structures.
And
Hi, everyone. I'm Susu. I'm Susu Xu. I'm an assistant professor here at Stony Brook University in civil engineering. My specialist is on sensing and smart cities.
great. Thank you. Well, let me, I do not know if we can see the participants. Can we see the,
No, not in webinar.
not in webinar. Very good. Well, then I will go ahead, and we have a little bit of some presentation, some slide material that we will share with you. And then we will be turning that on and off to have just a conversation with you all. So let me share my screen. No, over here. I will share my screen here. And see. There, I believe most all of you should hopefully be seeing our slides.
Yes, perfect.
Yes. Okay. So again, welcome. We are faculty from the Department of Civil Engineering, and we wanted to talk to you about the city of the future, and hopefully get you interested and excited about the many possibilities that are upon us right now, and certainly, of course, looking forward, and how civil engineers are going to be central to this new future that we will have to address. So, the question is, I don't know if you have wondered, what will the cities of the future look like? And how will engineers be involved in defining what that future will be, how that future will be created, and what will be the engineering disciplines that will contribute to that future? Of course, being civil engineers, we think that civil engineers will be at the forefront of this future, but absolutely we will not be doing it alone. There will be many other contributions, because this future, our future is likely to be very complex, requiring not only engineering knowledge, but also social and economical and other aspects of our knowledge base. But here today, I want to share with you how civil engineering could or will be part of this future, which we are defining right now. But before I go to that, upon preparing for this conversation with all of you, I figured that most of you are familiar with what civil engineering civil engineers do. So civil engineers plan, they design, they construct, and they operate what we call critical infrastructure systems. And I'm sure that you can relate to buildings, bridges, dams, ports as traditional civil engineering projects. These are very large, unique projects that make our society work. We rely on them to work properly. If they are disrupted, our normal way of life is severely disrupted. And therefore, civil engineers require a specific training to address this large investments from typically from public enterprise and sometimes private investors. So civil engineers not only are in charge of creating this environment, we are also in charge of protecting it. So for example, we need to protect our environment to ensure safety, quality of life, prosperity. With climate change, for example, we need to be able to design and protect our cities against the rise of sea levels. We need to make sure that we are prepared to deal with extreme events, whether that is a hurricane, an earthquake, a tornado, and accidents like the ones that could occur for the operations or normal use of facilities, which are in the bottom right image, you see a collision of a barge with a bridge that lead to a collapse. So these are duties of civil engineers that most likely you are familiar or you expected. And they are, of course, still very relevant and very important. But today we wanted to talk to you about the future. What will be the role of civil engineers in the future? And so then we start thinking about what will be our future civil infrastructure environment. And this futuristic image that you see on your screen now may mark you to pause and think about, amazing cities with large dense populations, transportation systems that have autonomous vehicles, the conservation and generation of electricity, environmental health, clean water, a sustainable environment so that we can take care of our living space. There are enormous challenges, but very exciting opportunities for the future. So if we think about that future, there has been a study that has identified the 6 trends that will change the future. And among the most, among those, the ones that resulted out of this analysis have identified alternative energy, autonomous vehicles, climate change, smart cities, high technology construction and advanced materials, and policy and funding as the 6 big items that will define what the future of our cities and the future of our civil infrastructure will be. I would argue that in all of those, civil engineers will play a crucial role. In alternative energy, from the design, operation, optimization of wind turbines, for example, or marine turbines, autonomous vehicles, the development of new roads, as well as new information systems and data analysis to control these vehicles. Climate change, addressing the rise of sea levels, the protection of erosions of our coastal areas, the design of infrastructure that is resilient. Smart cities, the development of of cities that provide safe environmental conditions for future large inhabitants, both in dense areas as well as suburban areas. Construction techniques that will take advantage of new automized techniques such as drones, 3D printing, and of course, policy and funding that will allow us to a sustainable way to do this. Again, all of these futures will require collaboration, and they are interconnected. So I share for you here, for example, and I will just illustrate a few things. These are the 6 emerging areas, and in the center, just as an example, there's climate change. So of course, climate change is one of the consequences that we know is causing sea levels to rise and more frequent extreme events. This will have an effect as to how we design smart cities for the future. It will have an effect on the development of advanced materials or use of advanced materials and development of high technology construction to make sure that our cities are resilient upon those climate changes. It will impact the way that we increase the use of autonomous vehicles or electric powered vehicles. It will promote the development of alternative energy sources. So all of these aspects are interconnected and will lead to great opportunities for growth and innovation and job activity for future engineers. And it will create jobs that most likely do not exist just yet. These will be new areas where that we will have to find solutions, where we will grow into. And this future is now. So, for example, this is a graph that shows a vision of what that future might be. So around the 2020s, which we are living now, is the concept of mega cities promoted by construction drones, the idea of batteries, energy storage. Towards the 2030s, we may start to see the development of rural cities, cities that people may not necessarily want to live in high dense urban areas, but they need to still be connected by high-speed transportation systems, the internet. They may work remotely. We may foresee the possibility that if climate change continues to lead to the increase in sea level in sea levels, we may consider the possibility of dealing with floating cities and how that future might lie, and the use of AI, artificial intelligence, may become prevalent. If our environment changes, we may want to explore or have the need to explore the development of frozen cities or environments in the extreme conditions. And of course, towards the 2060 and 2070, 50 years from now, the challenges and opportunities of developing dwellings and habitat conditions beyond Earth. This future is, even though right now it seems very stretched out and very futuristic, is happening right now. This is 50 years. And if you think about it, right now, civil engineers are designing infrastructure that is supposed to last 50 years or even more, 100 years. Are we going to get it right? Are we going to do the right things for the needs of the future? So in some ways, the future is now. So there are many exciting opportunities. And even though these are very futuristic ideas, we would like to share with you some of the things that are happening right now at Stony Brook University to make that future happen. So I will take a pause here. I will stop sharing and hand over the conversation to Professor Celli to share with you what he is working on. So Paolo.
Sounds good. And if you can put up the slides so that they will let me out.
Oh, yes.
So yeah, for example, in my case, I work in the, I think you have, it's right below, fantastic. Yeah, so I work in the area of structures, and I do so with a group of students that it's a mix of PhD students, master students, many undergrads, and sometimes even high school students, which have managed to do pretty good contributions in my group. So what I deal with is experiments and computation. So I do experiments and the build model related to unconventional structures. And with the, so can you please, I can do it. Okay. Perfect. So when you think of usually when you think of a structure, when you think of a bridge, for example, of the two images that you see there on the left, you probably think about the first. Something that is static, something that is built to last, not to change. But when I think of bridge, I think more of the second option, the one you see there at the bottom, which is a prototype of a deployable bridge, which is something that, as you can see, can be fabricated to be very compact and wheel-like, and then upon the utilization of some actuators can be deployed into an actual bridge, okay? So some deployable system, something that is capable of shape changes. So this is what I'm interested in. I do a lot of work in shape-changing structures, and to do so, I really try to come up with creative designs that feature arrangement of structural elements, even basic structural elements, but arranged in a way such that in concert, they produce some desired, very interesting functionality. For example, what you see there at the center of the screen is an assembly of cross-like structural elements that is fabricated to be flat. And then upon actuation can be popped up into a three-dimensional dome-like structure, as you can see in these images. And most of the research that my group does is, by the way, you can see that structure over here. This is a small-scale prototype of what you see there, which is a few meters by a few meters. And this is just a small-scale prototype. And upon the application of a pulling load at the boundary, you can pop up this initially flat structure into a dome. And this is quite of a novel concept that can replace provide an improvement on some of the lightweight structures that are currently used for stadiums, pavilions, and so on. But among the things that I do, again, pop-up structures is really a big thing. I try to design new and interesting structural elements. I deal with structures that are multi-stable structures. For example, and a classical example is what you see here is a slap bracelet, something that can exist in two configurations, one that is stowed and small and one that is long and can be used for several purposes. For example, these are very common in aerospace engineering to create tubular masts for spacecraft. But in our case, we're trying to use similar types of structures, for example, to create, I don't know, like coilable turbine blades, for example, for wind energy purposes that can be, transported in a compact configuration and then deployed on site. And finally, a thing that I'm really working on is environmental morphing. So trying to leverage the environment, changes in temperature, changes in humidity, in order to transform a structure from a certain shape to another shape. Okay, and do I have a little bit more time, or I don't know? Yeah. So basically, as far as shape-changing structures, this is really they're also going a bit more in detail. These are really called deployable structures, and you see them everywhere around you. They're everyday objects, toys. They're making their way. They're very common in aerospace to create, for example, foldable antennas, and they're making their way also in civil engineering, for example, to create morphing bridges, as I showed you before, morphing facades of buildings that can adapt to the environmental conditions to let sun in or not. And another big push, as I told you, is this of environmental morphing. And my dream would be that of creating a structure that somehow I can put out there in a dry day, and then due to changes in humidity, it pops up into a second, it self-constructs in a way, into a second popped up shape, and stays in that shape no matter what the conditions are afterwards. So these are some of the things that I have in mind and some of the things that I'm working on. Of course, for all these things, the work that me and my students do is very fundamental in nature. So we try to come up with this concept, test them at the tabletop scale, and then see if there is a pathway for their applicability to larger scale applications. But yeah, so this is pretty much what I do. I don't know if I ran through it, and I don't remember if I. Oh yes, another example is that both even Dr. Burgueno is working on is this idea that trying to flip the script in structural engineering. While in the past, for example, and still nowadays, people were really afraid of the idea of buckling. Buckling is really when you have a column that under a very large weight buckles, so undergoes a very large lateral deformation. And buckling is very dangerous to be avoided, except that nowadays we're trying to use this idea of buckling, for example, to trap energy. What you can see there on the right is an example of a structure with an egg on top, and the structure is capable of buckling within it, and it can trap some of the energy associated with a free fall type of motion and prevent an egg from breaking, for example. And Dr. Burgueno is using some of these ideas to create devices that can trap some of the energy associated with earthquakes, so that these devices capture the energy and the structures don't break. this is pretty much what I have.
Thank you, Paolo. We will hand it over to Susu.
Can you see my screen?
Yes.
Okay. Hi, everyone. I'm Susu Xu. I'm an assistant professor. My background is actually pretty multidisciplinary. I have background in both civil engineering and computer science. And the research field I'm working on here at Stony Brook is actually also very interdisciplinary. We especially have a group on civil infrastructure system, having me and Dr. Anil Yazisi and Dr. Wen Qing. We all work on this civil infrastructure system, combining with the emerging technologies, including autonomous driving, smart mobility, computer vision, these and other advanced artificial intelligence technologies to make our civil infrastructure system smarter and more efficient to better serve people's daily life and also under the emergency response scenario. So here I show a figure of a typical view of current city, and you can see that these civil infrastructure systems actually are the foundations of our city, supporting our daily life, like our mobility, our living, and our just built environment. So you can see some typical civil infrastructure systems like buildings, transportation system, these bridges, these civil infrastructures, and also the environment. All of these kind of critical infrastructure systems are what we really care about. And the problem is that as now we have more population moving into the cities, and we have this growing, more complex human mobility, and we have more challenges like climate changes. So all of these kind of challenges actually result in more complex interactions between this civil infrastructure system and human and also the environment. So as civil engineer, we couldn't just design these civil infrastructure systems just built based on our past experiences, but we also need to consider its interactions with these more complex, more dynamic environment, and that push us to these frontiers of leveraging this big data in the cities and understanding the data from human and from the environment to better design and operate and maintain our civil infrastructure systems, which now we call as smart infrastructure systems. So some key elements in these critical infrastructure systems are mainly about the sensing and the machine learning. So basically now, except for the physical component of this civil infrastructure system, we also start to deploy a lot here on the vehicles, on the buildings, on the bridges, on the roads, on the traffic light. Almost every types of infrastructure system you can see, they are mounted with some types of sensors. And in the meantime, we collect the real-time data over the entire city about how people are moving, what is the status, how these buildings are vibrating, how these bridges are vibrating. We collect this information so we can utilize artificial intelligence and machine learning technologies to better understand the dynamics inside the infrastructure system or the entire urban systems. Like you can understand their conditions, where is the traffic congestion, where is the air pollution, where is the noise, so I can do a better maintenance and management about the entire city. So that's basically how we're now in this smart infrastructure system, how we retrieve the information from these infrastructures and how we make decisions based on this information. And especially my research is a collaboration or collaborative integration of the sensing, artificial intelligence, and actuation technologies. We develop different theories and algorithms by collaborating with experts from electrical engineering, from computer science, from statistics, to apply this kind of theory and algorithms to real-world applications such as the daily urban monitoring.
We can monitor the air quality, the traffic congestions, the bridge health, the building health, and we can also do the emergency response. For example, when disaster comes, when the slow change, this climate change comes, how should we better improve our infrastructure system to make them resistant or resilient to these kind of dramatic changes? So we deploy our systems on, can see some examples. We deploy them on the railway, on the bridges, and we keep monitoring the vibes of the cities. And here are some examples we have done. One is this environmental sensing. So we mount a lot of vehicles with these kind of air pollution sensors. When they move inside the city, like the ride sharing services or taxis move inside the city, they collect the data and share data with us. So we can basically utilize this data to construct the map of air pollution and conduct the real-time monitoring. For example, these are some information we collected from these vehicles about the air pollution. And if you keep zooming in, you can actually get a lot of detailed information here. Sorry, I think there are some problem with my animation. And another application is about the rapid disaster response we have done, is that we actually work a lot with USGS and NASA on leveraging this advanced sensing technology together with the remote sensing to better understand that when disaster occurs, for example, earthquake or hurricane or flooding or wildfire occurs, what are their impacts? How many people die? What about the human displacement? How many buildings are damaged? Which roads are blocked? So that we can better utilize this kind of information for the disaster or efficient disaster response. So basically also utilize this information sensed by the satellite, these optical images or SAR images, to infer where the damage is actually located at actually in a near real-time situation. So immediately we know where the damages are and we can better dispatch rescuing people to save the people there and better do the recovery process. And now we are also combining the data from social media. For example, the information you share through Twitter, through news, through Instagram. We all crowd this kind of information to better understand the situations of human, where people may be trapped. So we utilize this information, we extract this information to better organize the recovery process or response process. And so from this process, you can also see it is a very interdisciplinary field. You will need the knowledge about the critical civil infrastructure system. You need to have the knowledge about how people are using these infrastructures. We also need to have the background in or the knowledge about the computer science so that we can better utilize algorithms to help us extract the information. And yeah, basically that's what we are working on in Stony Brook University Civil Engineering department, especially our group of civil infrastructure systems. We are basically designing and deploying these advanced technologies to better understand and better maintain and manage our civil infrastructure system and also have them better serve for people's needs. And I think that's my introduction. And Rigoberto?
Yes, thank you, Susu. Let me come back to this. So I'm sorry, my slides are not advancing. So the two examples presented by Professor Xu and Celli are just two areas of research that we do at Stony Brook University. Other areas include the evaluation of coastal effects, and I'm going to go back to this to avoid the text. Coastal effects on coastal environments, dealing with offshore wind energy and the design of these massive offshore energy clusters. Water quality, one of the biggest problems and the biggest achievements of our modern societies is the accessibility of clean water. And yet it continues to be a challenge to make sure that we have clean water and for everyone. And this is a continuing challenge because our way of life is introducing new pollutants and new chemicals into the system that we need to identify and then remove. But it, of course, is something that we expect and rely on, that when we turn on the faucet at home, that we are going to be safe and that the water that we consume is going to be safe and we don't have health concerns. So I hope that you can see that the future of our living, the future of our environment will very much be transformed by civil engineers. Now, this future will be multidisciplinary, as Dr. Xu mentioned, a combination of understanding mechanics and materials, computational power and algorithms, data, understanding satellites and programming, electronics and sensors, so that we can make buildings that feel just like our body does, and materials that heal themselves as our human body again can able to achieve. So at Stony Brook, we are aiming to become an innovator in the education of future civil engineers. We provide a curriculum that is founded on fundamentals, which is then applicable for the jobs of today, as well as scalable for the jobs of the future. We have student organizations that allow involvement in hands-on projects and connections to the industry. So some of our students participate, for example, in a concrete canoe competition. So you build a canoe out of concrete that it floats, and they compete on it, they row on it. So this is a very exciting and challenging project. We provide accessible research opportunities for undergraduate students at all levels, like Dr. Celli shared with you. And we believe that because of our small size, we provide attention like a private university at a budget of a public university. We have faculty expertise in different areas of civil engineering, hydraulics, coastal engineering, environmental, structural, and smart infrastructure systems. What do you need to become a civil engineering student and a civil engineer? Strong background and knowledge in mathematics, physics, chemistry, statistics and probability, computer programming, and built on those fundamentals, there's a number of specialty knowledge that is applicable to some of these nice projects that you heard from Dr. Celli and Xu. With that, we thank you for your attention, and we welcome any questions that you may have. I'm going to stop sharing the screen so that we may take any of your questions.
Yeah, so everybody here, you could put your questions in the chat. So, and I'll ask our panel the questions. So if you have any questions about anything, regarding civil engineering or something that they were talking about in terms of the research and the projects that are, being done here. One of the questions that students often have is how hard is it to get involved in research? Like, if a student wants to get involved in research, that's a civil engineering student or someone in the College of Engineering, and they're sort of looking at areas that fall into your areas of research. What would a student usually do? Like, what would be the process?
So I can answer this since I have quite a bit of experience with undergrads in my group. Usually, it only takes a question. It only takes students to reach out to a faculty, and at least in my case, but others as well, we're very open to the possibility of working with undergrads. In my case, when I receive an email, I always give them full consideration, and most of the time I say yes to whoever asks, and that's why my group is rather large at the moment. I would say that we give also opportunities. We have events like in our department, the open house, which is really designed to get students to come to our labs, talk to us, see what we do, inquire about research opportunities. For example, we had an open house a month ago, and there was a student that came up to me saying she was interested in research opportunities, and that started a conversation. So it really doesn't take, at least with us, we're very few, right?
But
So
you may want to share the range of levels of the students that work with you.
Yeah. So I worked from high school students, freshmen, sophomore, juniors, and I would rather not to start doing research projects with seniors because it's a little late. So I want time to work with students so that they can get the most out of this experience. But yeah, so one of the students in my group right now, she started research with me as a high school student, and then she came to Stony Brook, and she continued the research since freshman year. And we have great opportunities at Stony Brook. We have the Eureka program that funds summer research opportunities. I believe it's around $5,000 for a 10-week summer internship of research with one of the professors here, and last year I had 4 Eureka students. So these opportunities are there.
That's terrific. And, just so students know, Eureka is a program called, it's Undergraduate Research and Creative Activities. And it's the ability for us to connect students with research that's currently going on campus. It's specifically designed for undergraduates. Obviously, you don't have to go through Eureka for that if there's other opportunities around that are not part of that you want to get involved in. But just to let you know that we do have something specifically for undergraduates to get involved in undergraduate research. One of the things that comes up all the time, and you mentioned this, was the emphasis on science and math, especially math. We're always preaching that to the students that are interested in Stony Brook, especially in the STEM areas. We usually are telling students to don't pass up the opportunity to take physics. We have a lot of students who might be interested in a lot of different areas like chemistry, and they want to take AP chemistry, but we're always telling them, no, make sure you take physics and calculus in high school. And those are the things that we actually weigh our freshmen coming in, our new incoming freshman classes. We're weighing their admissions on how they're doing in physics, how they're doing in calculus, obviously how they're doing in their other academic subjects, but making sure that they're taking calculus and physics. Would you say those are the most challenging classes, those initial ones for students? No?
I think that physics, math, and chemistry are very important, all of them. But I think the important thing is that they're not impossible. They are important because they provide the basis for students to understand the engineering applications that follow up later. I was talking recently with a mathematics professor at Stony Brook. And their perspective of mathematics is quite different than an engineer. Right? We use the mathematics to solve a problem or to understand a theory that leads to an application, but we're not constantly solving equations just for the sake of solving the equation. But there's a range. It depends on your discipline. Dr. Celli, physics is very important for the research that he does because he wants to understand how structures propagate stresses as they move, as they deploy. Dr. Xu uses a lot of statistics and probability for the evaluation of data in her models for artificial intelligence and machine learning. I really like chemistry because I'm interested in developing new materials, and I want to understand how these materials can be changed even at the nanoscale so that we can create smart materials that can heal themselves. So I say that these are the knowledge. If I were go back to my high school self, I would tell myself to take more chemistry, right? But I talked to Dr. Celli and he says, no, more physics. And maybe Dr. Shu says, no, more probability. So it really depends. But they're all
Yeah, it's very interesting because you all three have a certain flavor and dynamic of civil engineering too, because one is going from, like you said, the probability statistics and those types of things to I was looking at the bent structures, like you were using those, how they would actually withstand, or prevent, let's say, a collapse or more strength to a structure, which is really interesting. So
I think that for the students joining us, it's important to realize that the civil engineering is very broad, and it has many different branches that that one could follow as a career or for the further study. And then there's the interconnection with other disciplines that is becoming more and more common. I believe that there are many very exciting careers of the future and innovations that will require the multidisciplinary training that Dr. Shu was mentioning between, for example, sensors, which are produced by electrical engineers, of course, and then civil engineers that actually need to work with electrical engineers to understand where to deploy those sensors, how to use the data. And then with computer scientists to develop algorithms to efficiently use this massive amount of data and make sense of it. So there's a lot of interconnections and many different branches.
So some of our students are a little on the quiet side here. So I want to thank you all for everything that you've, that the whole presentation and just being here to talk to our prospective students. And thank you so much again for taking your time out. Thank you to the students for joining us today too. And I know finals are coming up this week, and so you're all busy people. So I want to thank you again.
I would say a final comment for the students who joined us today. If you have questions about anything that we talked about today, or about Stony Brook or civil engineering at Stony Brook, do not hesitate to look us up on our webpage. You can find our profiles and our faculty, description. Send us an email if you have questions and on anything we said today or about civil engineering in general. Whether you are considering Stony Brook or not, we will be glad to help you.
Great. Thank you again. And I wish you guys a smooth week this week with finals, and have a great holiday. Same with everyone here. Have a great holiday. Stay safe and talk to you soon. Take care.
Thank you.
Bye.
Have a good night.
Bye-bye.
Bye.
Right.